All right. So should I?
Maybe we can wait for a minute or so.
Sounds
for
good.
people
Yeah.
to just get into the
Let's wait until the participant stabilizes, and then we can start. All right, looks like it's a good time. Welcome everybody to the first distinguished lecture series hosted by the Center of Responsible Machine Learning in UCSB Computer Science. Today it's my great pleasure to welcome Professor Thorsten Joachim, who's a professor in Cornell University in the Computer Science Department and Department of Information Science. And Thorsten is a world leading expert in the field of machine learning and theory and algorithms. And he has gotten his PhD in the University of Dortmund in 1997 and then joined Cornell in 2001. And Thorsten has also spent some time in Carnegie Mellon University working with Tom Mitchell. The research area Thorsten focuses on, like he's super known for his remarkable work on the theory and algorithm in machine learning, including ranking, bandits, causal inferences, counterfactual reasoning, and so on, and with a lot of applications in search engine recommendation engines, as well as his recent effort in mitigating biases and ensuring fairness in machine learning-based systems. So Thorsten is a collector of awards and recognitions, and he's an ACM fellow, a AAAI fellow, a Humboldt fellow, and in particular, many of his research work has started the entire research area right after Thorsten wrote the first paper. So typically you'll see people having a number of best paper awards. Thorsten had 9 best paper awards in all the leading machine learning conferences and 4 test of time awards. So Thorsten is really the one of the most leading expert in machine learning that we have nowadays, and it is our great pleasure to have Thorsten talking to us about his recent adventures in fairness in ranking. Thorsten. Oh, yeah. I forgot to say the ground rules. Sorry about it. So Thorsten just told me that he welcomed questions during the talk. So for those who have burning questions, please type them into the Q&A chat box. I'll alert Thorsten from time to time so he can address those questions while they are still on time, right? And you could also save your questions towards the end where we have more time for Q&A.
Thank you very much for you, Jiang, for the very kind introduction, and thank you, William, as well for the invitation and the opportunity to speak here. So yeah, what I want to talk about is recommender systems, and in particular ranked recommendations, and multiple aspects of what actually a ranked recommendation system should be doing, and rethink a little bit the history of these systems and adapt it to the types of problems that we actually have today. And that's going to lead us both to biases, but also to just general design questions around fairness. So this is work with a number of collaborators and students. And I'm particularly going to talk about kind of one line of work that we've done on policy learning for fair ranking policies. So rankings are everywhere these days. And really, these types of ranking policies, you can think about them, they take in some context, could be a query, could be a user profile, and they output a ranked list of items. You know, that comes up in a search engine here, that comes up in many e-commerce sites, media streaming, you typically have even two-dimensional rankings, that's the layout that we have. Or the kind of news feeds that we get are typically presented as rankings. So I think it's quite obvious that the way that we rank items has a big influence on what gets seen and what gets purchased and what information gets distributed. So, you know, let's start by thinking about where this whole field of ranking and ranked retrieval or ranked recommendation is actually coming from. And then let's think what that actually means for today. So that's my starting point. So, you know, the field of ranked retrieval kind of started in the 60s. It kind of came out of library science, where the goal really was to help people find books in a library or help an analyst find information to write a report. And then I would say there was a lot of development, but then there was a phase transition somewhere around 1994, when the first search engines actually brought this technology of ranked retrieval into kind of the real world, right? Into people's living rooms. They brought it into commerce. And since then, you know, these kind of ranked interfaces have taken the world by storm, and there's lots of different applications where rankings now are present. Now, the field started as, you know, helping people find books in the library, and that was really clear what these systems were supposed to do. They were supposed to provide maximum utility to the users, to the people typing in the queries, people wanting to find books in the library. And it's very clear. Now, is that still the same today? Is this really the goal that these systems have, right? And if we train them with machine learning, which we do for virtually all of these ranking policies, is this what we should be optimizing, right? Or what are the goals that we should actually be training our systems for today? Okay, so let me start with the, you know, maximizing utility to the users. Now, clearly, one thing that changed when we did this transition from, you know, finding books in the library today is that the applications that we have today are really two-sided, right? So if I think about a retailer here, Etsy, and this is a query that I actually typed myself. I wanted to find metal table legs because I wanted to have a table for my home office. And I think eventually I actually bought something that looks a lot like this here. And so that provided utility to me, right? I found metal table legs that I wanted. But of course, there's also the other side, right? There's the providers or the producers of the goods on Etsy that also draw utility from the system. And so in particular, when I buy something on Etsy, that seller makes money, right? That's revenue for that seller. So clearly, there's utility to me as a user, but there's also utility to the seller, right? To the other side of the market that this platform mediates. Same thing for music streaming, right? I draw utility from, let's say, my Spotify rankings. To be precise, that actually my kids draw utility from my Spotify account. I actually use Amazon Music because I work for Amazon Music too. But same thing, they draw utility from this. But there's clearly also the other side. It's the artists, right? Every time something gets streamed, an artist actually gets streaming revenue. So by presenting rankings in a particular way, or presenting particular items high or low in the rankings, we are not only making the users providing utility to the users, but also providing utility to the artists. My final example is maybe close to home is, scientific papers. We wrote this paper recommendation system for the KDD conference last year, where we wanted to recommend papers to the participants. And clearly the participants, they drew utility by finding papers that they wanted to read or talks that they wanted to go to. But there's also utility to the authors, right? We all want our papers to be read, right? So where we present something, provides utility to the authors, they get their voice out, and eventually, that's important for getting tenure. So all of these systems are actually mediating a two-sided market. So from that perspective, I would argue that we need to think about both sides when we train our rankings. But maybe, maximizing utility to one side of the market, maximizing utility to the users, already provides us with kind of good utility to the items, right? Maybe that kind of happens naturally. This kind of conventional view of what we should train our recommender systems for is maybe best encapsulated by what's called the probability ranking principle. And in 1977, Robertson identified that, hey, really for basically all reasonable performance measures for ranking, ranking documents by their probability of relevance actually provides maximum utility to the users. So I'll put the document that's most likely to be relevant in position 1, the next most likely one position 2, the next most likely one position 3. And so I would argue that that is still the thing that's optimized by virtually all learning algorithms that train ranking functions, right? They try to optimize some form of DCG, NDCG, some precision recall, something like that. And these are all measures of utility only to the users. But the question is, if you do that, do we actually provide good utility to the items or the providers of the items as well? And so let's look at a couple of cases and see whether this is true or not, right? Should we just maximize utility to the users and then everything's fine? So here's the probability ranking principle here. And here's a mocked up example. Let's say we have a recommender system for candidates where employers can go and search resumes of candidates. And let's say for a particular query here, software engineer, this is what our system presents. And let's say our system knows exactly what the relevance is. And here relevance meaning the probability that this person will be kind of invited for an interview by an employer that has that query. So there's no, it's completely, so this is known, it's not learned. So, if you look at this, you'll see that there's a lot of really highly qualified candidates for this job or for this query. And that you get a disparity, right? So the person who happens to be in position 1 is Adam here. And he just has a epsilon better probability of being interviewed than the second best person. And heck, you can go all the way down to position 100, and he's still just epsilon better than everybody else. That means, if you think about it, that actually all of these candidates have almost equal merit or relevance for this query. But what's happening is that Adam here gets very high exposure, meaning he's going to be seen by everybody, like all the employers. He's probably going to get lots of invitation for interviews. And the people who are further down this list, at some point, employers just stop looking and they're not going to be found. So the exposure of somebody in position 100 is probably going to be very low. So there's this disparity now that, independent of the merit of the candidate, exposure can be very different, right? There's only an epsilon difference here, but the exposure difference is huge. Now, I constructed the example that it actually, if you look at the names here, all the stereotypically male names are at the top and all the stereotypically female names are at the bottom. What actually happens here is that there is a systemic bias against women. And that there's maybe just 2% of the employers that just don't interview women for a software engineering position. Now, what's happening here? This 2%, this small bias gets really amplified by our system, right? And so over time, what our system is going to do, it's not going to mitigate that bias. It's really going to amplify it. And that's something we certainly do not want, right? So maximizing utility certainly doesn't seem only to the users, certainly doesn't seem like a good idea here. Here's another example. This is artist recommendation, let's say for music. So here I don't have a query, it's just recommendations for me. And it has exactly the same numbers here, like the probability that I will enjoy this artist, that is my probability of relevance here. And again, let's say that's fully known. And artist one, actually I have a pretty eclectic taste. I like a lot of things. So I'll probably, find artist one and artist two up here, but I'm not going to find these artists down here. So again, there's a disparity that even though these artists are almost equally good, these people up here will make a lot of money. These artists down here, although they basically have equal merit, will get a very little share of the streaming revenue and are probably going to be driven off the out of business. Again, that's not fair, and it's probably not what the streaming service wants, right? They actually probably want to maintain a broad repertoire of artists, right, that produce good music. And maybe my last example of where just maximizing utility to the users and ranking things by probability of relevance to the user fails is this news system. So let's say we're a news aggregator, and on our front page we want to present like a list of top news articles of the day. And let's say we have articles from the Times, which is left-leaning, and the Review, which is right-leaning. And now we have almost 50-50% left-leaning and right-leaning users, but maybe the left-leaning ones, there's just 1% more. What that's going to mean is that all the Times articles are going to show up in the top 10 or so, and all the right-leaning Review articles are not going to show up. Well, what are my right-leaning users are going to say is that website is biased, probably rightfully so, right? And they will probably abandon the service, right? And so the service not only is now accused of bias, it also kind of lost half of its readership. So again, maximizing utility only to the users doesn't seem like a good idea. So I think what's fundamentally broken in all of these examples is that there is no kind of fair relationship between the merit of the items and the amount of exposure that they receive from our recommendation policy. All right, so that's the setup for the talk. And what I want to do in the rest of the talk is think about how can we mitigate? What are alternative criteria that our recommender system should actually be optimizing so that we mitigate some of these problems that are identified in this example? And kind of the key premise that I have is that a fair ranking policy should allocate exposure. That's really, that's what a search engine or recommender system does, is it's a way of allocating exposure based on merit. And that kind of relationship between merit and exposure should be fair, and we should actually constrain it to be fair. And there are two kind of failure cases, at least two failure cases, where this can break. The first one is that we have some endogenous factors that are kind of built into the design of our system. And I would argue those were the cases that kind of happened in the previous examples. There was a break between the merit of the items and the exposure that we allocated to them. That certainly has a fairness problem, but it actually also has a legality problem. So I think that first example where that system was basically discriminating against women was that actually would probably violate the 80% rule that qualifies actually that you could be sued for discrimination, for labor discrimination here. And more generally, I think, in many of these other cases, in addition to being unfair and probably ethically not right, you also generate market dynamics that you don't want as the provider of the platform. You don't want to create superstars, right? Because superstars mean that you're dealing with monopolists. You don't want to polarize, right? Because that means that you're actually losing part of your customer base. So these are kind of design questions that we need to get right. And then there's also exogenous factors. And those are biases that come into our systems, or biases that our systems generate on its own. And that's also something that we have to deal with. And so I want to address both sides here, the endogenous factors, the design factors, and the exogenous factors. How do we deal with the biases? So let me start with the endogenous. So I've said that we want to allocate exposure. I actually now need to formalize what I mean by exposure. And here's the simple model that we used. It's the position-based exposure model. And it basically says that or I'm just going to say is that, if I put something in position 1, the probability that somebody's going to see it is E1. If I put it in position 2, it's E2. And the further I go down, the further that probability goes down. And for any particular application, I have these probabilities, and they determine kind of the probability that the item will actually get discovered. And so the exposure of that a ranking Y for a context X or a query X provides to a group of items, let's say the female or the male job applicants, is just basically the sum of these exposure probabilities. How can we get those? Certainly you can do eye tracking experiments, but you can do this much more simply. There's little interventions that you can do that you can even estimate these kind of remotely. So basically little swaps that you can do to estimate these exposure probabilities in a very seamless way. So, but let's not worry about how to do that. Let's just assume we know these. Okay, so what do we want to do now? So we want to make sure that the exposure, as defined on the previous slide, is proportional to merit, or a function of merit more generally. And so our goal is that exposure becomes like a function of the relevance, which we could use as our criterion for merit of that group. And this function f specifies this relationship. So for example, we want to make it proportional or proportional to the log of it, or so. That's the f is a design choice, and it depends on the application. And it's probably something that you really have to kind of build consensus around. So if you pick f to be proportional, or the identity function or a constant, then what you get is that you just say, okay, exposure between two groups should be proportional to their merit. And you can write this now as a disparity that says, in how far is this relationship that we want between merit and exposure, how far is it violated? And so the disparity, the greater it becomes, the more violated is the fairness, so to speak. So that's how we're going to quantify unfairness, disparity. And so kind of conceptually, what we want to now do is we want to still maximize the utility to the users. So basically our learning problem is find me a ranking policy pi so that in expectation over the queries, the utility of the rankings produced by pi is maximized So that's what we always, that's our traditional kind of criterion that we do in learning to rank. But subject to the constraint that the disparity, the unfairness, is less than some constant delta. Delta is something that we can pick. And we can see later that actually there's a trade-off between utility and disparity. So that's what we want. This is our goal. How do we actually achieve this? How do we turn this into a practical machine learning algorithm? Well, we do empirical risk minimization. We search the space of all possible ranking policies that have good utility on the training set. And utility here really could be any rank performance measure, DCG, whatever, could be anything at this point. We'll have to specify it later to make it tractable. But subject to also an empirical constraint on the unfairness, on the disparity. And since it's kind of hard to optimize kind of constrained risk minimization problems, what we'll do is we'll actually replace this constraint by a Lagrange multiplier. And that's the usual trick here. That's equivalent by picking the right Lagrange multiplier. So basically what we get is when I'm optimizing an objective that's sum of the utility to the users and lambda times the unfairness to the items. How do we actually do that? So I said we are going to search the space of our ranking policies. But how can we search a space of ranking policies where ranking policies actually produce these discrete things that are rankings, and there's exponentially many of them? How do we actually search this space? So here's the trick that we're going to use. We'll actually think about ranking policies, and that goes back also to other learning to rank methods. And I think the first one to introduce this was soft rank. But we'll do it in a somewhat different way here. The trick that we're going to use is we're going to make our ranking policies stochastic. So basically, each of these pies here, so given a query X, context X, the probability of a ranking, we'll specify what the probability of ranking is, and then we sample policies from that, sample rankings from that ranking policy. So it's a conditional distribution. And you can think about it in the following way, that there are many different rankings that we can present. But now the learning problem just becomes, how do we assign probabilities to these rankings, right? And that's something we can change in a smooth way. That's something we can do kind of stochastic gradient descent on. And so that's going to be our trick for making this training problem tractable. And clearly, things like utility, we can still define an expectation. So if this is a probability distribution, then really just the utility of a policy is just the expectation of utility over the rankings kind of weighted by the probability of being produced by that policy. And you can also talk about exposure that a particular group gets for a particular ranking policy, right? That's just, where do items from a particular group get ranked, right? For example, the exposure of item A under the stochastic policy is, with probability, 52 plus 20, so 72, it gets put into position 1, right? It's these two cases. With probability 25 or 23, it's in position 2. And I think the last 5%, yeah, is in position 3. Right? So now that we have kind of made our space of policy smooth, we just have to pick a parameterized space of ranking policies. And then we can use kind of optimization methods like stochastic gradient descent for them. And the particular space that we use are Plackett-Lusch ranking policies. Plackett-Lusch model is particularly easy to deal with. It's basically that what you put into position, so you learn a score. It's like the softmax version of a, sort your items by score. You learn a score for each item, or you have a score for each item. And then instead of deterministically putting the highest scoring item in position 1, you pick it with a probability that's proportional to the score. You pick the item that goes into position 1 that way. Then you take that out, and then you pick, again, proportional to the score, the item that you put into position 2, 3, 4, and so on. Right? That's the Plackett-Luge sampling model. And now by tweaking the scores through things like stochastic gradient descent, we can learn different ranking policies. And the way that we come up with scores, our scoring model here, that can be anything that's differentiable and produces a number. And typically we'll use like a neural network for that. So how can we then do stochastic gradient descent for that? We'll basically use tricks from reinforcement learning, in particular policy gradient. So it's it's difficult to get a closed form solution for the gradient for the Plackett-Luge model. But you can use Monte Carlo estimates of the gradient and then do kind of a reinforced type stochastic policy gradient kind of optimization. And you can use the standard tricks that people in reinforcement learning use for these types of problems. All right, let's look at what this gives us. So what this gives us is, so here's some experiments. So we call this algorithm fair PG rank for fair policy gradient ranking. So this is on a kind of synthetic data set. It's based on the Yahoo Learning to Rank challenge. And we here we actually have like individual fairness. So it's every item is its own group, right? So we want to kind of ensure that every item gets kind of exposure that's proportional to its merit. And so what you get here is that if you change this trade-off constant lambda between unfairness and utility to the users, then you can trade the two off. So basically, if you crank up the value of lambda, your model becomes more and more fair until basically the unfairness converges to 0. But you do pay a price in terms of utility. Right, it's no longer the optimal utility maximizing rankings, and so you can pick the trade-off of what you find acceptable between the two. So this demonstrates that you can actually train learning to rank algorithms to not only optimize utility to the users, but you can also train them to optimize fairness to the items, where the fairness criterion is something that you can specify. So that does address this left-hand box, right? At least for a particular notion of what it means to be fair, right? We've designed our ranking policies in a way that we kind of want them to be. We want to provide some degree of fairness to the items. But let's also look at this other box, the exogenous factors. And so far, we've assumed that somehow we actually have ground truth relevance judgments that are not biased at all. How do we, but that's not typically what we train on, right? What we typically train on is biased data. And one particular type of bias, there are many different ways they can be biased. So there, as I said before, maybe there's actually bias against certain groups, like discrimination against female software engineers. But one bias that I want to focus on is what's often called the position bias, and that's actually a bias that our system generates itself. And I want to talk about how we can at least address this one, even though I don't fully understand how to address the other ones. So no, normally we don't have ground truth data. Somebody gives us examples of what's relevant and what's not. What we typically have is some kind of behavioral data. So we may have click data of the following form. From our system that's running, we may have, there's a policy that's currently deployed, and we've presented, we've gotten a query, we've presented a certain ranking, and then we observe clicks in that ranking. That certainly provides some information, right? The clicked items, that's a relevant signal, right? But it's also probably going to lead to biases, right? And how far is it going to lead to biases? Well, whatever we present, or whatever our current ranking policy does, and whatever it presents high in the ranking, is probably going to get the most clicks. So if there is a systemic kind of way that items were disadvantaged in the past, and our policy reflects that, then what's going to happen is that it's really hard for items that are down here to ever bubble up to the top, right? Basically, what you get from these kind of click feedback is a rich get richer dynamic, right? What's at the top gets even more clicks, gets even more positive feedback, and gets even more highly recommended, right? And so on. And that's how you're creating these, superstars or winners take all. So, and that's different from the previous problem, right? It's not a design problem. It's really a problem of that we're not interpreting our data, that our data is biased, right? So let's think about where this bias is coming from and how we could actually model this. And then once we understand that, we can hopefully get rid of it. So this position bias, where we presented something in the past, it comes from two factors, right? If you want to observe a click, then you only observe a click if people actually look at that item and if they find it relevant, right? Both things have to happen. And if both things happen, you get a click, right? That's a very simple model of how people actually click in a ranking. And that's all good, right? If you see a click, you know that the person must have looked at it and found it somewhat relevant. And I'm using click as a stand-in here. There could also be a purchase or a long click where people didn't back out immediately, right? Some signal of positive signal of relevance. So that's all good, right? There's a two-sided relationship here. But where's the problem? The problem is that if you don't see a click, it could be due to two reasons, right? The first reason is it's not relevant, it's bad, doesn't have merit. Or the person just didn't see it, right? It was too far down the ranking, didn't see it. And if we learn from this data and we conflate these two reasons, right, then that's what creates this rich get richer dynamic, because we can't tease apart the two reasons here, right? That the person didn't see it versus didn't like it or didn't find it relevant. So what we really need to understand is this observation mechanism. And it turns out that it's actually very close to kind of a fairly typical causal inference problem where you have a selection bias. So, and we could use techniques from causal inference to correct for this selection bias. Ideally, we would think that we would need to know whether the person, whether person A looked at a particular result. That would certainly help, right? But it turns out that it's already sufficient to know the probabilities or the propensities of observation. You don't actually need to know whether it actually happened or not. And let's call these observation propensities Q. It's the probability that in a ranking Y bar for a context X, the user will look at a position at a particular position J. So that's another random variable that we can't observe, but we know the probability of yes or no. How can we use that? Well, we can use inverse propensity weighting. That's the simplest way of how to make use of it. And it's a very simple idea. So if we, for example, want to estimate the utility of a ranking, according to something like the discounted cumulative gain, which has this nice additive structure, basically where we say, okay, if you put a relevant or click document at a certain rank, we get a certain score for that. Now, if we know that if you put something in position 3, only half of our users look at position 3, then what IPS weighting says is every time you do actually see a click on position 3, upweight it by 1 over 0.5. So that means we're kind of correcting for the fact that we're missing half of our data here by every time we do see a click, we're actually counting it twice. Or if we know that something is in position, only gets observed as position with probability 20%, we're upweighting it by a factor of 5 every time we do see it. And it's a two-line proof to see that this actually gets you unbiased estimates. Right? An expectation we're doing the right thing now. And we're correcting for this presentation bias, even though we don't actually know exactly where the person looked. We only know the probability of looking there. And with it, we get unbiased estimates of utility for this additive utilities that are of additive form, like DCG. And we can also estimate like an overall marginal utility for any of the items or any of items in a group of items. So what this basically does, it makes our relevance estimates independent of position, at least in terms of bias, not necessarily in terms of variance, but in terms of bias. So how can we turn this now into a machine learning method? Well, basically, we can still do empirical risk minimization. What we just do is our training error now gets replaced, or training utility gets replaced by this IPS estimate. It's an unbiased estimate of utility, just like we typically have an unbiased estimate like training error. And also this disparity term, if you think about it, that is also something that we can now estimate in an unbiased way. And so we can just basically, again, do empirical risk minimization of this weighted objective, just like what we've done before. So, and again, we can use the same tricks. We can use the same policy gradient tricks that we've done before. Things get a little bit more complicated, but I'm glossing over this. Basically, it still works out. Okay, let's look at how that works. So first, the question is, with enough of this biased click data, do I still eventually converge to the same kind of quality and fairness of my rankings that I would get if I actually had completely perfectly labeled data? So full information is where we actually know the true data. It's basically the algorithm that we had on in the first half of the talk. That was trained on full information data. And if you look at this, it's this curve, this dash curve down here. And this is a trade-off now between unfairness here, so lower is better, and utility further towards me here is better. So you really want to be in this bottom left corner, bottom right corner. That's kind of the optimal spot. That's kind of where you want to go. And what you can see is the amount of training data that you give to this algorithm that we call filter for fair and unbiased learning to rank. If you crank up the amount of biased click data, it does actually converge to what you would get if you had perfect data. So this removing the selection bias actually converges to the kind of full information case. Let's compare this to a couple of alternative ways of how you could produce fair rankings. The first one is kind of the group blind one. So this is actually on data that we've done. It's kind of synthetic data. It's based on the Microsoft Learning to Rank benchmark. And we just picked one of the attributes and called that group. So we have two groups in this case. So the first kind of naive approach to kind of trying to be fair to the two groups is to just not give the group assignment to the group attribute to the learning algorithm. But it's well known that that doesn't work, right? So you actually get something that is unfair, right? It doesn't have unfairness 0. So that group blind doesn't work. The second one is maybe this one. the red one here, that's using that algorithm from the first part of the talk, and we just ignore the fact that we have selection bias and that clicks are biased by position bias. And we just call everything that has a click, we call it relevant, and everything that's not clicked, we call it not relevant. Now that clearly doesn't work. If you crank up this lambda parameter between maximizing utility versus fairness, it actually does just the wrong thing, right? If you crank it up, it actually makes it less fair. And that's because you're estimating your unfairness, you're estimating your disparity in a biased way, and then you're enforcing like a biased unfairness measure, which doesn't make sense, right? The other alternative is there's post-processing methods. This is the one by Biega et al. We have come up with one as well, where you basically first try to estimate relevances, and then you do a post-processing and try to turn those into a fair ranking, kind of ensuring fairness of exposure. But the problem here, they also have a kind of a parameter here that kind of cranks up how much you want to enforce fairness. But you see, you can crank it up as much as you want, and you don't get down to zero. You don't get down to being completely fair. And the reason is because the first step, we used an unbiased estimation method for estimating these rankings. But it's only unbiased with respect to the presentation bias. It's not unbiased with respect to the two groups. So if you actually analyze it, it's much better predicting relevance for one group than for the other. And so because fairness is not, or group-based fairness is not part of the underlying estimation method, the post-processing method also does the wrong thing, basically. So the argument that we're making here is that if you want to ensure fairness, you actually have to train end-to-end, where, from the beginning, as part of the whole estimation process, the whole system needs to be aware of kind of unfairness right from the beginning. And so these last two curves this is a linear filter model where, you start with something that's has a lambda equal to 0, you crank up lambda and it goes down to 0. And this is not a linear, but it's a multi-layer perceptron model. So that actually gives you better utility, and you also get down to unfairness of 0. All right, so I think there's a lot to do in this space. This is really just one design criterion here that we can have in terms of fairness. We haven't even talked about fairness to different user groups, for example. And we've only talked about one of potential bias that we want to mitigate, that's position bias. But there's certainly a lot more that we need to take into account. And to just get you thinking about the complexity of these problems, let me just mention kind of the types of recommendation problems that I think we're going to see more and more, and that are already people are already doing. For example, in recommending in drop recommendation. And in these types of problems, we're actually really mediating one of the kind of vital societal institutions, right? And correctly, there's lots of safeguards that the law actually imposes on what you're allowed to do when it comes to employment. So when you think about recommender systems in this space, you get these highly complex problems. And so, on the one side, you have the applicants. On the other side, you have the employers. Both sides have preferences in this case, right? It's not just that the applicants have preferences over the employers, what we typically had, right? The users had preferences over the items. No, now kind of the items, which are the employers, also have preferences over the users, right? And so, we need to think about what these systems should actually be optimizing, right? We have multi-sided preferences. We certainly need to be fair to the applicants. We also may have certain kind of policy goals for the employers. And certainly there is now also, so each of these drives utility from it, but there's also a social welfare component that these systems have, right? That they, we as a society have an interest in, for example, ensuring low unemployment. So the question is, how do we take all of these conflicting goals that a job recommendation in this matching market would have and make sure that they're fulfilled? So, we've started to look at these problems. And maybe what I just want to say is that by explicitly optimizing for some of these maybe social welfare objectives, you can actually do substantially better than a naive ranking system that just maximizes utility to the users. But on the other side, you also have to now deal with issues that, like individual utility, like to a particular applicant, some people do better. Actually, a lot of people do better under the system that optimizes social welfare. But there's also some people who do worse, right? How do you trade off the social welfare improvement in a fair way against, that some people are actually worse off under this social welfare maximizing policy? So I think these are really interesting and profound questions that we as people who actually design these systems need to be at least aware of, and that I think we want to design the systems in the right way. So I think that's, it's a big research agenda. And I think, I want to stop here and if there's questions, if there's discussion, I'd be happy to take that. Thank you.
Yeah, thank you very much, Thorsten, for the excellent talk. So we're moving to the question and answering section. So we'll start with Tim's question. Tim, yeah, actually.
So maybe I just read it myself.
Okay.
Related to the first half of the talk, can everybody see the question, or is it only me who can see the question? Let me just read it. Related to the first half of the talk, all of these examples seem to assume that there is a single well-defined merit defined for an item. In many problems, there are multiple dimensions of merit, and we may not know ahead of time how to combine those into a single score. They may not be related at all, or they may be uncertain. There may be uncertainty associated with how they are combined. Some of these problems with utility maximizing rankings an artifact of projecting this much more complex space down to a single dimension of merit. For example, if you're looking for a metal desk legs, there are many factors, including cost, style, height, durability, seller's trustworthiness, etc. Does the idea that maximizing relevance is the best ranking still hold when there's uncertainty associated with the merit function itself? Would increased exposure to the more diverse Pareto frontier make more sense? Yeah, I agree. I think in particular, the issue of uncertainty, I think, is really underexplored in rankings. And I think these are, there's actually, you're touching on a whole bunch of different issues, like there's multiple objectives that we have. Often comes up in diversity, right? That we are actually not certain about what the objective or the intent of the person is, right? And that we want to hedge against different intents. But let me just kind of pick on that aspect of uncertainty, right? I think one thing that's very intriguing is that whenever we estimate a ranking function, there is actually there's always some uncertainty about the estimated relevance for a particular item. And we typically use point estimates. But especially when the uncertainties between different items are very different, then you run into issues where maybe you have a lot of data for some some group of items. You don't have it for another group, this gets kind of regress to the mean, so typically ends up with a lower score. These get, you get accurate estimates for those. And so you're actually not reflecting that, for these items here, you have substantial uncertainty that, hey, they may actually be better, right? But since you're kind of risk averse in your in the way that you're estimating you're actually estimating a mean, you're actually not conveying that uncertainty. So I think there is actually a kind of a big issue in not modeling uncertainty in this ranking problems and not conveying uncertainty. And that actually creates an issue of unfairness as well. So for example, if you have substantial more uncertainty about a job applicant, right, that applicant could be better, or that you haven't evaluated a particular type of job applicant, thinking about mechanisms that would actually make employers incentivized to explore kind of regions of the kind of space where they are where they're not knowledgeable, so that you don't get these disparities where some people are just or some items are just not ranked highly just because we don't know anything about them. So I think there's lots of interesting problems in this space.
Yeah, that's a very interesting point on uncertainty. Let me pick on that question before getting to the second question into the Q&A. So Thorsten, you talk about how you can make an existing data set and use it and with IPS and empirical risk minimization so that you can actually learn a fair policy for ranking items. But you didn't tell us about like how you collect those data sets in the first place, right? So in reality, it is an online kind of a recommendation and feedback, and recommendation and feedback, and all the users will provide all these clicks, and you are developing the next policy according to that. How are you addressing exploration?
Right now, exploration is actually not addressed at all, and there's again potential for kind of long-term versus short-term unfairness, right? You don't want to, the exploration comes at a cost to the users. So there's a short-term cost, but there's also a long-term gain, right? By getting more information about them. So thinking carefully about how to allocate this cost of exploration in a fair way, I think that's another really interesting problem that's actually not at all touched on here. I fully agree. We've actually, we did actually look at this in. There's a current paper that I'm not sure I'm violating rules. I don't want to talk about it. So there may be submission rules that I'm not supposed to talk about. Yeah.
Well, yeah, it's still kind of nice. You're learning a randomized policy, so some of that like might be easily encoded into the end-to-end system, right? So let's get to the next question. Telling us that when there are multiple platforms, recommendation system competing for the same set of buyers and sellers, how that might limit affect the practical extent of fairness.
Yeah, right. There, like on top of these, the kind of market that each of these platforms generates, there's this additional kind of global market of how sellers move and how customers move. I think there's very interesting questions around that. So I think there's one interesting piece of work that I want to point out in this space is to actually work also done here at Cornell by John Kleinberg and collaborators, is thinking about, if all of these systems kind of use the same methodology, we'll get to a point where these systems become more and more homogeneous, right? In a sense, the recommendations that they make become very similar. And what does this actually mean for something like, if everybody uses the same job recommendation system or job screening system, that this creates a kind of monoculture where you don't have multiple trials basically at there's always some randomness, but now the randomness is no longer independent, right? If you currently apply to multiple employers, they make somewhat independent choices. But if they all use the same system, you don't anymore, right? So that could create issues. I think actually, so some of these things around fairness, if you are a platform provider, and I think you are very interested in maintaining a kind of a healthy population of both of your providers, let's say your sellers on Etsy, and your customers, right? And it's important to get the balance right. If you are having a few sellers that make a lot of money, and that a lot of other sellers are driven out of the market, your inventory is going to shrink. And in the long run, your customers are not going to like that, and they're going to leave, right? So, but on the other hand, if you're providing maybe bad recommendations because you're actually recommending bad items, then your customers will not find what they want and they will leave, right? So how do you actually trade these two off, right? So that you kind of maintain a healthy market where both sides are kind of in equilibrium and are stable, right? I think that's a really interesting question.
It looks like there's a meta-level sequential decision-making problem that requires many dimensions of considerations to be taken into account. Very intriguing problems, Thorsten. Maybe one last question before we let Thorsten go. Tao asked about the experience of applying the fair ranking algorithm for the news ranking problems you mentioned at the beginning.
Should the fairness measure be query dependent?
Right.
So there, I think anything that happens in a query independent way. My example was there, okay, what should you show on the front page where there's no personalization happening? That's basically query independent. So there's no customer profile or so, it's not adaptive. If you make it dependent on some attributes of the customer, I think you still get similar problems, right? Maybe then you have, you present different rankings for customers from, let's say, different states, if that's the only thing that you can observe. I think even within that population, you still have potentially a fairness problem, right? And you can kind of drill down and get smaller and smaller segments. At some point, you get perfect personalization, then maybe these kind of fairness of exposure issues go away, at least in a polarization type of sense. But I think you still have these issues even at moderate levels of personalization.
Awesome. Yeah, this is actually a very, very interesting point. As your example point out that they may differ by a little bit in terms of the total, say, click-through rate. But if you're maximizing utility throughout without depending on the individual queries, then you are always going to be pick the one that is only 0.01% better. Right. On the other hand, if you personalize, and then maybe the relevant score for different group of users will be different, and both of them will be served in a more fair way. So I think that's
true. So I think some of these issues go away if you have really good personalization. But I think even when you get there, there's probably an argument to be made to at least have some diversity in there, that you're not kind of actually represent the diversity of a particular user's taste. Even though maybe these types of fairness problems that are addressed by this method go away.
All right. Yeah. Thank you very much, Thorsten, for the excellent talk, and thanks everybody for asking insightful questions. And let's give Thorsten another round of applause. And thank you for giving the distinguished lecture at the Center for Machine Learning, Responsible Machine Learning. And typically, when you are physically here, we'll present you a little token of appreciation. But now we'll just ask Laura to mail it to you. So please provide the mailing address for us.
All right.
And thank you again. And look forward to inviting you to Santa Barbara physically sometime soon.
That would be nice. Thank you. Thank you very much. All right.
Thank you.
Bye-bye.